In this video, we're going to investigate a little bit more the behavior of RL circuits. We have a resistor, we have a self-inductance given here by the presence of the inductor. I mean, it could be self-inductance. This could actually be an inductor. Just like this could be self-resistance, I guess if you want to call it that, or it could actually be a component. Either way, the circuit's going to behave the same way. We saw in the last video that we're going to expect behavior similar to a capacitor problem, an RC circuit. And that's because this inductor is going to oppose the current change. Not the current, but the current change. Sometimes it could oppose the current, sometimes it could try to boost the current. And it does that because of the induced field in the coil and the changing flux if the current is to change. And so what that does is it makes the current take some time to ramp up and some time to ramp down. Okay, so first thing I would say is let's close a switch and let current begin to flow. What is going to happen? Well, as current starts to flow around this circuit, an EMF will be induced in the coil, which seeks to oppose the current. How would it oppose it? Well, the polarity of the EMF is going to have to be reversed from the battery. It's like hooking up a little bitty battery oppositely. It's like hooking it up, moving from positive to negative instead of from negative to positive. I'm not actually hooking up a battery, but that's the idea. And so what I'm saying is we expect, as we move across the inductor, there to be a voltage drop, and we expect it to be negative. Why negative? Because it's opposing this battery. Notice if I'm going to analyze this with a Kirchhoff's law analysis, if I draw my analysis loop like this, I'm going to get a positive voltage from the battery, but if this is opposing, that means I have to get a negative voltage drop across here. And then if I'm moving with the current, as I've drawn the current like this, as I go across the resistor, I know that I'm going to have a negative voltage drop across there. So if I do a Kirchhoff's analysis of this, I get this equation: battery EMF minus the EMF induced in the coil, which I know is L di dt, minus IR is equal to 0. This is just from a straight Kirchhoff's law analysis. Now, before we talk about the solution to this, I want to take a brief aside and talk about energy. Because what we have said is there is an EMF induced in the coil. That is, there's a voltage across the coil. Well, what is a voltage but an electric potential? And what is an electric potential but electric potential energy per unit charge? You don't get a potential without having some sort of potential energy. So there's energy in the inductor. What we say is that the energy is stored in the field. That actually turns out to be debatable, or it turns out that there's some debate among scientists if that's the case, but we're at least going to go with it for here. And that's usually what I would think, is that the energy is stored in the field. And so what we can say is that the field, of course, is going to be characterized by the circuit and the inductor itself. So we can write down this equation. Your book goes through a simple derivation of this equation, which feel free to follow along with. They're always useful to do, but I'm going to give it to you here. The energy stored in the inductor is 1/2 Li squared. Now this hopefully should be a little familiar. We saw something look like this a few chapters ago. Energy stored on a capacitor is 1/2 CV squared. Of course, there were some other expressions of this, but the point is these have the same flavor, and they exist because of basically the same reasons. I'm storing charge on a capacitor, therefore I'm storing potential energy. I'm not storing charge here, but I am moving charges. I have a current, therefore I have a magnetic field, therefore I'm storing energy in the field. And so I just want to introduce this to you quickly. This is the potential energy stored in an inductor. Of course, if the current's changing, the energy is changing. This is the expression for when the current is fully, when the current is steady, I should say. Just like this is the energy when the capacitor is charged. If this were at some intermediate point, I would probably write a lowercase I to symbolize that it's a function of time, but it would still work. But just wanted you to see this expression. Okay, now let's go back to my Kirchhoff's law expression. If you look at this, this looks really similar to the equation we got when we did a Kirchhoff's law analysis of an RC circuit. It's a first order differential equation. The good news about differential equations is if you solved one of one form, you've solved all of the other ones that have the same form. So we're going to use that and just, I'm kind of hand waving here, we're just going to write down the solution to this. Because in one sense, we've already done that. I encourage you, if you're interested, go back and look at the derivation of the charging capacitor equation. It's going to be really, really similar to this. In fact, I'm going to use that result to write down the expression here. Not charging, though. There's nothing charging, but I did start off the discussion saying we turn on the circuit, we close the switch, and the current starts to ramp up. This is just like what happens in a charging capacitor. But what I get out of this is that the current as a function of time is equal to this, the EMF divided by the resistance, as it has to be, 1 minus e to the negative RT over L. Make sure that's, there we go. And that is the solution to this equation, and this is what we would, I wouldn't call it a charging inductor, but it's the equation that describes the current as the inductor is coming up to full field. Right? There's an EMF that opposes the change, which is why I get this exponential nature in the first place. Now, what we did in case of RC circuits was I took the constants that were in my exponential and I redefined them as some characteristic time, the time constant tau. Remember, tau for capacitors was RC. I'm going to be able to define a tau for inductors, T sub, or not T, tau sub L is going to equal L over R. So I had T over RC for my capacitor. I now have RT over L. I still get T over tau. So I can actually rewrite this expression in terms of that characteristic time as E over R, 1 minus E to the minus T over tau. And that is really, well, it's exactly the same as my charging capacitor equation. It's just that in this case, I have a tau sub L instead of a tau sub C. But the behavior we're going to expect is going to be exactly the same. We're going to get an exponential nature out of this. We looked at those graphs in the last video. The current's going to ramp up to some final value. And then this is not the expression for it, but we'll see later that the current will ramp down to 0 when you turn it off. And in fact, I can write down that solution now. It's going to look exactly like the discharging capacitor solution, which is this, E over R times E minus T over, that's a T, that's a tau sub L. Just like the discharging capacitor, only in that case I had the tau C, which I didn't subscript as a C because it's the only tau I had, but now I've got to subscript this with an L. So they follow the exact same form. We expect the exact same behavior. The reasons, of course, are different. I've got an inductor instead of a capacitor, but the form of these expressions are exactly the same. So the good news is we're really familiar with those and we know how to manipulate those.